I've got a sort of, it's actually my own tie. I've got sort of a pretty Christmas tie to celebrate the season, but also to remember, again, victims of human trafficking. Always remind yourself of that. We do have our exam coming up soon, our final exam. I'm going to remind you when that is. Our exam is going to be the last day of finals week, Friday, December 19th, from 8 o'clock till 10:15. That's actually starting about 15 minutes earlier than most final exams in that first spot. I'm wanting to give you a little bit more time. You can use an entire sheet of paper, front and back, to write stuff on for the final exam. I'm not going to give you sample problems because I reuse old final exam problems, but I will tell you what types of problems to expect on the final exam. Probably tomorrow, actually. I'll send you a note about what to expect. It is a little bit more than the midterms. They're each worth 14%. The final exam is worth 18%. It is cumulative, though there is a heavier emphasis on more recent stuff from chapters 15, 16, and 17 on the final exam. It is also more conceptually focused, less computationally focused than the midterms were. Not that there aren't computations, of course there are computations on the finals, but there are a lot more conceptual geometric problems where I give you some graphs and you need to decide how to interpret something. For example, a bunch of level curves and gradient vectors could be an example of a picture that could show up on the final exam, and you need to understand what's going on. All right, so today we're focused on understanding more about vector fields and integrating vector fields. They're called line integrals. And starting Wednesday, I'm also going to talk about something called Green's theorem. And I hope I can find a green shirt and a green tie. Actually, I've only got one more tie from a student to wear, so if anybody else wants to still give me some ties tomorrow, that would be great. I'd like to wear something green to celebrate Green's theorem. Today is sort of the backdrop. Before we get to Green's theorem, we need to talk about line integrals more, and in particular focus on vector line integrals. So again, there are three main applications that we're thinking about. Mostly we're thinking about the first two. First, the work done by a force. Secondly, to measure circulation of a fluid around some closed-oriented curve. Closed means it comes back to where it started. Less of an emphasis, but perhaps easier to understand, actually, is measuring the flux of some, say, two-dimensional thin sheet of liquid as it passes through some one-dimensional membrane. Flux is a measure of unit of, well, in that case, area per unit of time as time goes by. When you think about the vector field as modeling a flow of fluid. That's probably easier to understand, but you should realize that's not the same kind of line integral as the first two. And today I'm going to focus on the first two. Probably on Wednesday we'll have a little bit of time for the flux. We need to focus more on the main application. The main applications need to work in circulation. All right, so I talked about work a little bit at the end of class on last Friday. Let me remind you what I said. First of all, at the most basic level, when you're applying a force in the same direction as motion, just pretend that was in one direction. I moved a little bit. I apply a certain force in newtons, a certain amount of distance in meters, and I get the work done by that force as the product force times distance. This being in newtons and this being in meters. So the work is going to be in newtons times meters for the units. That's the same as joules, which is a unit of energy. So you are measuring, in a sense, how much energy you went into pushing that table over that distance. The floor is also applying a force to the table. And when I move it at a constant speed here, the forces equalize. They're canceling each other out. The work done by the floor, when I'm moving the table in that direction, is actually negative, the negative of the work that I do in moving the table. And the total change in kinetic energy is zero because the speed is constant. If I do increase the speed, it goes faster and faster, pretend, say at a constant acceleration, then the net force is positive. I am applying more force than the floor is applying in the opposite direction so that I accelerate the table. In that case, the net work is positive and the change in kinetic energy is positive because it's going faster as you go. All right, in a slightly more complicated case of applying a constant force not in the same direction, say I'm pushing at an angle as I move the table, draw some kind of picture like this. If the displacement is thought of as a vector, call it d vector, and I apply a constant force, which I'm drawing as a bunch of different vectors. I mean, these are all the same vector as far as the length and direction goes, but it's different positions. If I apply that constant force as it moves, the work done in that case is a dot product, F dot D. Remember, dot products are numbers. There were still some people on exam 3 who were forgetting dot products are numbers. Always remember that from now on. Dot products are scalars or numbers. This can be interpreted as the length of F times the length of D times the cosine of the angle between them. And since the cosine is a unit function, that could be thought of as either a positive or negative angle. If you rewrite this product as the length of F times the cosine of theta times the length of D outside the parentheses like this, that also emphasizes that you can think of the work done as the component of F in the direction of D times the distance traveled. So it really is an analog of this. This expression here, the length of F times the cosine of the angle, is the component of F along D. So this product, again, is analogous to that. This component of F plays the role that F did back here. And the length of D is the same as that. All right, so that's what you do in a constant force situation. What about non-constant forces? For example, gravitational forces, where, say, you're focused on a comet going around the sun. Let's pretend the sun is right here. And you've got a comet going around the sun. It goes very far away before coming back. That comet is, you're modeling its motion by thinking about the gravitational field that the sun generates. Of course, there are other masses, Jupiter, the Earth, etc., that do affect the gravitational field slightly. But for the most part, the gravitational field along the comet's path points directly toward the sun. It's actually longer when it's close to the sun. I'm making it look like they're the same distance from the comet to the sun. That's not the case, but these are going to be longer over here than they are over here. These are going to be pretty short vectors over here. But they're all pointing toward the sun. They're supposed to all be pointing toward the sun, even if I don't draw it perfectly. So that's a force field generated by the sun's mass. It's gravitational. And the comet has mass as well, and so they attract each other according to Newton's laws. And we've seen via Mathematica that you follow an elliptical path. That's, again, Kepler's laws show that. But we use Newton's laws to prove Kepler's laws. Anyway, what's this like in the context of talking about work done by a force? So the force now is this force field. F is a gravitational field. In fact, you can even write a formula for it. If r is the position vector from the sun to the comet, with the sun being at the origin of the coordinate system, then we've seen you can write this force as negative g times the mass of the sun times the mass of the comet, divided by the cubed length of r. And the reason we cubed the length of r is because we're also multiplying by r itself, and with a negative sign there to indicate that the force vector points directly toward the sun, from the comet to the sun. So we need it in the opposite direction as the position vector of the comet. The unit vector in that direction is this vector, which is why we end up having an extra factor of a length of r there. So even though you see a length of r cubed there, it really is an inverse square law. We only see a cube there because of this extra unit vector that comes into the equation. M is the mass of the sun, capital M, and lowercase m is the mass of the comet, capital G is the universal gravitational constant. That is the gravitational field. That's what the comet feels, so to speak. What's the work done by that gravitational field? Well, because it's not a constant gravitational field, you need to imagine thinking about small chunks of work done over small paths that the comet travels over. So let's say the comet starts right there at a certain moment in time, and a little infinitesimal amount of time goes by, dt, and the comet moves slightly, ever so slightly, to a new position. Let's imagine zooming in near here. Here's a zoomed in picture. Make it slightly slanted. So that's the path of the comet over an infinitesimal amount of time. Its length we've called ds. But we could think of it as a vector, ds actually. Let's go ahead and write that as a vector. And the length of that vector is the ds without the vector symbol. What's the force field look like there? Well, it's a lot longer than this. That's an infinitesimally small vector. You can barely see it, right? That's what you're imagining. It's so small. The force field, that vector is not infinitesimally small. It's going to be really long. I'm out of room on the board. Pretend it's right there. But in reality, it's going to be much longer, in your imagination at least. What's the small amount of work done, dW, by this force with respect to this change in position of the comet? It's the analogy with that. It's the force dotted with the vector ds, the vector symbol. So the total work done by the force field on the comet over any non-infinitesimal distance traveled can be found by adding up the little works, right? There's a conceptual equation. It's not rigorous, it's a conceptual equation that helps you understand where the formula comes from. We're integrating over some oriented path. Here's C, is our oriented path, say, from here to here. And it's traditional to put the C down there. And then you go ahead and replace dW with f dot ds. So this encapsulates the idea of why work should be calculated this way. What's the practical way to calculate it, though? You need a parameterization. Again, this needs to be an oriented curve for vector line integrals. For scalar line integrals, it doesn't matter. So you need to pick your parameterization of C with the function c of t, where t goes between a and b, based on the given orientation. The orientation in this case is based on the direction of motion of the comet, counterclockwise. Once you've done that, you can informally figure out how to represent this in terms of c of t, and its derivative, in fact. You can do some informal calculations. You could replace the ds with ds dt dt, and this is the velocity vector, which in terms of the parameterization is c prime of t. You're going to integrate with respect to t. You need to evaluate the force field along the parameterization, along c of t. So ultimately, you need to plug c of t into the vector field f, dot it with c prime of t, put a dt here to indicate you're going to integrate with respect to t from a to b. So ultimately, this can be written as an integral from a to b of this thing, f of c of t dot c prime of t What's hard about this? Typically the hard thing about this is finding the parameterization, finding C of t. That's the hardest thing about this typically. And in fact, with this example, you have to find C of t numerically. We had to use ND-solve to approximate the path of the comet. So you're not going to have a formula for C of t in this case. You have to approximate it. So with this particular example, you have to think of this more numerically, in terms of numerical approximations instead of formulas. But as far as book type problems that you will get on the test, it's actually pretty easy. I mean, doing this integral is pretty easy once you've got C of t. Typically, these things don't involve square roots. It's not like the scalar line integral. This dot product for a typical kind of example is typically pretty simple. Polynomials oftentimes. For example, consider the vector field you see here. I want to write that down. That's not a gravitational field. It's just a made-up example vector field that I actually made up randomly, somewhat pseudo-randomly in the last class. F equals xy cubed plus x comma x plus y squared. And I picked C of t to be t comma t cubed. That's the parametric curve that I picked. That's going to parameterize the curve y equals x cubed. Essentially, I'm just replacing x with t. And so therefore y gets replaced with t cubed. I did it from -2 to 2 in the last class. I think I'm going to do it from just -1 to 1 in this class. So this is the part of the curve this is the curve we're parameterizing. The orange curve is starting at -1, and going up to 1, 1, as t goes from -1 to 1. I got the vector field in the background. I don't want to try to draw that by hand. I want to use my technology here, vector plot in Mathematica. I'm going to zoom in closer to the origin now. Let's let x and y go between -1.5 and positive 1.5. We'll see the vectors better that way, hopefully. And I'm going to let the curve here go from -1 to 1. There we go. That is better than the picture in the last class. Now, we can pretend this vector field is a force field. You know, your typical force fields come from masses giving you gravitational fields or electric charges giving you electric fields. Is it possible to create some force field that looks like this? I have no idea. If I had to guess, I'd say no, but we'll pretend here. So we'll pretend this is a force field, and we'll pretend that there's some particle moving the force field like this. Of course, the particle, or the rocket, if you prefer, probably is going to have to be producing its own motion, so to speak, if it is going to move like this, because probably the force field wouldn't cause that to happen naturally in the absence of some other force. But we're just focused on the work done by the force field itself, ignoring other forces on this ship, say, as it goes from this point to this point. That would be given by doing the line integral. The line integral is going to give you the work done by that force. The function that you integrate, well, what's the velocity vector? That's pretty simple. What happens when you plug the position vector into the function? That's still pretty simple, though getting to have a high power of t there. What happens when you calculate f of c of t dot c prime? That period represents a dot product. You get something still pretty simple, though you're going to have a high power of t. T to the 10th plus 3 t to the 8th plus 3 t cubed plus t, if I put it backwards from mathematical representation there. What will the value of the integral be? I could just go ahead and copy and paste this part in. Or once I have its formula, I can copy and paste that in. That integral will give you the answer. Should I expect it to be positive or negative? We haven't talked about this yet. Should you expect it to be positive or negative? Well, remember, dot products are positive when the angle is between 0 and 90 degrees, and they're negative when the angle is bigger than 90 degrees, between 90 and 180, if you're defining the angle to be between 0 and 180. So imagine taking dot products of this force field, F, with velocity vectors along this curve that are pointing this way. Looks like the force field's pointing in this direction over here, this direction over there, so it's kind of hard to tell where it's pointing here. That's unfortunate. It looks like, generally speaking, the force field is pointing in the same general direction as the velocity vector up here, so I should expect positive contributions to the work done up here. It's harder to tell down here. I'm going to guess positive, but I could be wrong. Thirty thirds, excuse me. So a little less than 1. If the units for force were in newtons and the units for distance were in meters, this would be in joules, which is a very, very small amount of energy that probably is not reflective of what's going on with the spaceship. Is there any other way to get the answer? Well, you could use a different parameterization. That's probably worth mentioning. I could change C of t. Instead of t comma t cubed, I could do t squared comma t to the 6th. Still t going from, well, no, that's not going to work. Squaring is not going to be negative. I could do t to the 3rd, t to the 9th. As t goes from -1 to 1. The formula for this thing is going to be different. Look at that. It's got a t to the 32nd power involved. However, the integral should be the same. The integral of that thing from -1 to 1 should be the same, and maybe here's where it's unfortunate that I picked -1 to 1. I would have to change the limits of integration if I picked a different interval. Yep, 28/33. Let's try doing the original one from -2 to 2. From -2 to 2, the integral is that. This integral from -2 to 2 is not the same thing. Okay, why not? Well, when I go from -2 to 2 with the original parameterization, the point itself is going from -2 comma -8 to +2 comma +8. So when I use that new parameterization, t cubed comma t to the 9th, I want to go between the same 2 points. So I can't let t go from -2 to 2. Instead, I have to let t go from -cube root of 2 to +cube root of 2. Since t is being replaced by t cubed. So if I do make that change, make this a -2 to the 1/3. By the way, the negative is on the outside there. You do the 2 to the 1/3 first. At least on Mathematica, it matters. The 2 to the +2 to the 1/3. Now we should get the same thing. Yep. Okay, so we do have to make that kind of adjustment if we use a different parameterization like that. Is there any other way to do this integral? Not that I know of. You can approximate it in various ways. Because this vector field, this one right here, because I wrote it down basically randomly, I was almost 100% sure that it would not be conservative. What did conservative mean? Conservative vector field? By the way, there's no such thing as a liberal vector field. Okay? It's not that kind of conservative. There's no possible friction. Conservative vector fields do conserve energy. In the context of gravitational fields and electric fields, we're focused on mechanical energy. There's no possible function whose gradient is that. There's no potential function in all likelihood. Yeah. In all likelihood, there's no potential function. Actually, I know there's not. Is there a way you can verify that? When you pick vector fields at random, so to speak, in all likelihood, they will not be conservative. They will not be gradients of some potential function. By the way, potential functions are functions. They're not just potential functions, right? Corresponds to potential energy. What's a way you can verify that there is no potential function? Give this function a name there. Let's call that F1 because it's the first component of F. Give this one a name, call it F2 because it's the second component of F. Should remember from the very first section of chapter 16, there was a condition about what are called the cross partials. I haven't mentioned these in class yet. The partial derivative of the first function, the first component with respect to the second variable, and the partial derivative of the second component with respect to the first variable. Those partial derivatives are sometimes called the cross partials for this vector field. Again, because you're kind of crossing the order of the component with the order of the variable. This is the first component, that's the second variable. This is the second component, this is the first variable. That's the reason they're called cross partials. If you look in section 16.1, you'll see these. In section 16.1, I should tell you the page. Page 942. There's a condition, a theorem that says, assuming your function is nice and conservative, assuming there is a potential function, then these cross partials will be equal over the entire domain. They will be the same function. The contrapositive of that theorem says that if these are not the same over the entire domain, then the function is not conservative. There is no potential function. So that's pretty easy to check. Are these cross partials equal or not? Partial of f1 with respect to y is 3xy squared. Partial of f2 with respect to x is always 1. These are not the same function. And that's the issue. They're not the same function. They are equal for some values of x and y, like for example, if y is 1 and x is 1/3, they'd be equal. But they're not the same function over the domain. Therefore, that theorem in section 16.1 guarantees that this vector field is not conservative. There is no potential function. Don't bother trying to find it. How do you make conservative vector fields? Calculating gradient vectors is the main way to do it. So here I've got another function. V is a scalar valued function, not a vector field. X cubed times y squared plus 3x. What's the gradient of V? Differentiate that with respect to x, get 3x squared y squared plus 3. Differentiate it with respect to y and get 2x cubed y. That, by definition, is going to be a conservative vector field. Watch what happens when you integrate a conservative vector field. Well, I have to tell you what happens, basically. We can't really watch it. Here's the function itself. Here's its gradient vector. Let's see. Let's go in closer to the origin here. I'll go back to my original C of t. comma t cubed. Oops, I forgot the curly braces here. Okay, there is the, this looks different than the one in my last class. Something seems different about this. Okay, I'm not sure why it looks different from the last class, but let's go with it anyway. So what are we seeing here? Assuming it's right, we're seeing the level curves of V. We're also seeing the gradient of V. Notice the vectors are normal to the level curves, point in the direction of increasing values of V toward the lighter regions everywhere that you see them here. Relatively small in the middle, so you don't see them very well. We've got the same parametric plot, same C of t as before. Let's put that into here as well. E comma t cubed. Copy and paste the parametric plot. We're integrating this new vector field over this curve. Again, this new vector field is the gradient of a function. This is the function we integrate. You can see it's 3 plus 9 t to the 8th. Here's the integral. It's 8. I claim there's a much easier way to find the answer. Actually, this one's not too bad. It's a pretty easy integral, but there's an even easier way to find the answer. Anybody do the reading ahead of time from section 16.3? Want to tell me what the easier way to get that answer is? Do the reading? Well, you could sure earn some brownie points if you did the reading. It is a good idea to do the reading. I'll emphasize this enough. Especially now. This is stuff you really, really want to do the reading ahead of time for. It's going to make the class go much better for you as far as understanding what's going on. Nobody? Okay, well, the integral can be calculated as a difference of values of the potential function. Just like regular integrals can be calculated as difference of values of antiderivatives. When there is a potential function, it is kind of like an antiderivative. You can calculate the value of the integral by doing a difference. It's v of the ending point minus v of the starting point. Q is the ending point. P is the starting point. Q is 1, 1 in rectangular coordinates. P is, excuse me, yeah, that's the ending point. QP, the starting point is -1, -1. So we've got to plug those numbers into V. We can do that by hand. V of 1, 1 minus V of -1, -1. Plug in 1, 1, get 4. Plug in -1, -1. I bet you get -4. Yeah, you do. There you go, 8. So when you've got a potential function, it's easier to do it this way, to do the integral that way. When there is no potential function, then you've got to use the parameterization. In fact, if you think about this, we never use the curve at all here. The fact that it's that particular curve evidently is irrelevant. All that matters is the starting point and the ending point. That's P, that's Q. I could have done something like this for my curve. And evidently, I would have gotten the same answer. I think on Wednesday, I'll show you examples of such things. If you use trig functions, you can make pretty wavy curves. And evidently, I would get the same answer. Amazing. It doesn't matter what the curve is. This is called path independence. And conservative vector fields are path independent. Doesn't matter how the rocket got from here to here. The work done by the force field, the gravitational field of the sun, is the same. The total work on the rocket, which also comes from the thrusters, is not necessarily the same, but the work done by the sun is the same. The gravitational field of the sun. Work done by the thrusters could be different because the rocket could be going slower or faster at the end than it would be otherwise if it was just following the gravitational field. All right, so that's called path independence, and that's pretty important. How do you know you can do this stuff? Could I prove it? It's actually not too hard to prove. I'm not going to write sentences, but I'll write some equations that should be convincing. So here's the integral that you always end up doing in this context when you use the parametrization. If f is conservative, that means there is a potential function. F is the gradient of some function v. Take a look at that integrand. Does that seem familiar? Like from chapter 14, maybe. Or actually chapter 13, I guess.
Looks like a version of the chain.
Yeah, it looks like something with the chain rule. The derivative of the outside function, specified as a gradient, plug in the inside function, times, so to speak, actually that's a dot product, the derivative of the inside. It's the chain rule for paths. This thing right here is d dt of v of c of t. This function, v of c of t, is a function with real number inputs and real number outputs. It's a calculus 1 kind of function. It's got simple formulas like 3 plus 19 to the 8th or whatever we got before. Yeah, I guess that's right. It gets there through vectors. You plug a number t into c, you get a vector, or a point if you prefer, in two-dimensional space. Plug that point into v, you get a number back. So it takes a detour through two-dimensional space, but overall, you've got real number inputs and real number outputs. This is a regular derivative. It can be calculated using vectors. But because this is the case, that means this function inside here is an antiderivative of this function up here. And we can use the fundamental theorem of calculus, FTC, to say this is v of c of d minus v of c of a, which is the same as that, because c of a is p and c of d is q. All right, so that should convince you, I hope, that this works. It is based on the assumption that f is the gradient of some potential function v. It's also going to mean if the curve we integrate over is closed, meaning we come back to where we started, what's the integral over such a curve going to be? For this kind of example. 0. P and Q are the same. V of Q minus V of P will be 0. So it's path independence and also what's called the circulation of the vector field around any closed curve is going to be 0 when it's a conservative vector. Which is then trying to get into fluid mechanics applications, though in a way that's not exactly clear as far as what the circulation means. Actually, we'll only be able to understand circulation real well for small situations where the curve itself is like a very small circle or something. Then we're going to end up using Green's theorem that I talked about at the beginning of class to understand the circulation for small circles. But how do you find a potential function if there is one? Let's pretend that we did not know that this vector field was a gradient. So I'm going to change this formula up here. I'm going to replace the f I had up here originally with a different f, this one that I've highlighted. 3x squared times y squared plus 3, 2x cubed y. Again, I've said if you sort of randomly write down a formula for an arbitrary vector field, in all likelihood it will not be conservative, it will not be a gradient of some potential function. So to pick a vector field that will be conservative, teachers always figure out a potential function first and then find the gradient. But what if I gave you this on the test and I said, well, determine if it's a conservative vector field or not, and if it is conservative, find a potential function. The first thing you should do is, again, check the cross partials condition. The derivative of the first component with respect to the second variable, and the derivative of the second component with respect to the first variable. In this case, you do get the exact same function. The derivative of f1 with respect to y is 6x squared y, and the derivative of f2 with respect to x is also 6x squared y. These are the same. Is that enough to guarantee there is a potential function? The answer is a qualified yes, and in this case, a definite yes. Point out a theorem in the book that answers this question. Look at the bottom of page 968, it's theorem 4. Page 968. It says, if your vector field is continuous on what's called a simply connected domain, and if the cross partials are equal on that simply connected domain, then the vector field will be conservative. There will be a potential function. But what does simply connected mean? The technical definition is given in the book in terms of deforming closed curves down to a point. I'm not going to explain it at the moment, but I'll tell you to read about that. What I'll say for the moment is in two-dimensional situations, basically simply connected means connected, first of all, it's all one piece. It's not two separate pieces to the domain. And secondly, it also means there's no holes in the domain. Your domain doesn't look like that, for one thing. It also doesn't look like, say, a disk with one point removed. Right? Even one point missing would cause the domain to not be simply connected. That's basically what it means in 2 dimensions. In 3 dimensions, it's not quite so simple, pun intended. Simply connected domain. The plane is a simply connected domain. The entire plane doesn't have any holes in it. That's the domain of this thing. That's simply connected. Therefore, the equality of the cross partials here does imply that there is a potential function over the entire domain. How do you find it, though? It's a matter of integration. Potential functions are kind of like antiderivatives, so it shouldn't be a surprise that you need to do some integration to try to find them. If there is a potential function, this first component, f1, will be the partial of the potential function with respect to x, and the second component, f2, will be the partial of the potential function with respect to y. So this is going to imply, for example, that the partial of v with respect to y will be 2x cubed y. Evidently, then, if I integrate that with respect to y, I will find v, at least up to an additive constant. V will be the integral of 2x cubed y with respect to y. I'm just writing it as an indefinite integral, because all I'm after is, effectively a derivative type of thing. This is going to be x cubed y squared plus c Should I write plus C? C could be a constant. It could also be a function of x. Because for this integral, x is constant. So there could be some expression involving x here that defines a function c of x. If you check in your head, differentiate this with respect to y, you'll get 2x cubed y plus derivative of that with respect to y is 0. So it should seem right because of that. We haven't used this fact yet, so we need to use that somehow. Well, we probably should differentiate this now with respect to x. Now treat the y as constant. Get 3x squared y squared plus c prime of x. Does that equal 3x squared y squared plus 3? Sure, if c prime of x equals 3. So if I set this equal to 3x squared y squared plus 3, I will get that c prime of x must be 3. So c of x equals 3x works. Or 3x plus some true constant, pi or something. Okay, don't do that. You don't need to. We're just after one potential function. Once you found one, there are actually infinitely many. Hey, look at that. It matches the original B. But yeah, I could have added on some other constant there originally too. So that's the method for finding a potential function. You will see that if the cross partials are not the same, and you try this method, it won't work. You'll be able to do the first step fine, but when you try to do the second step, finding this partial and setting it equal to that, you will see there's nothing you can pick for c prime of x that will work. You'll get c prime of x equals maybe something involving y, which doesn't make sense since c only depends on x. So you get stuck somewhere if you try to do it in the case of a non-conservative vector. Any questions about that? Couple minutes. Let me just end by summarizing where we're going to go from here. Again, on Wednesday and Friday, we will talk about Green's theorem, and you've got 2 more completion assignments, one due Wednesday, one due Friday. Green's theorem tries to look at all this and unify it in a sense. And I see there's sort of being 2 main roles for Green's theorem. One, it is a calculation tool for line integrals. You'll see that it allows you to calculate line integrals as double integrals, which sounds maybe harder, but is actually oftentimes easier because you don't have to worry about the parameterization. And it works for non-conservative vector fields as well. Another purpose of Green's theorem is to understand something called the scalar curl of the vector field, which is going to help us understand this idea of circulation, at least on a small scale. Okay, so that's where we're going, and that'll finish off the semester. See you Wednesday.